we were told that a small sample property that we might find desirable is efficiency. That is to say, that our least squares estimator has minimum variance in the class of linear unbiased estimator. So what's the theorem by which we prove that least squares is best linear unbiased? Named after two guys. So the Gauss-Markov theorem tells us that the least squares estimator is best linear unbiased. What's the strategy that we use in the proof of the Gauss-Markov theorem? What's the strategy by which we prove the Gauss-Markov theorem? Least squares is a linear estimator, right? So we have to invent another linear estimator, right? Yeah, because that's what the Gauss-Markov theorem says. The Gauss-Markov theorem says that in the class of linear unbiased estimators, least squares has minimum variance. And so what we need to do is invent another linear estimator that's unbiased and prove that it has a bigger variance. So you'll see in your notes that you got off the web that the trick is to create a new estimator, beta star, and do that. Isn't that a linear estimator? C is an arbitrary matrix of constants. N, oops, let me put in some parentheses here. So we just change, the least squares estimator is a weighted average of the observations on the dependent variable. So if we're just inventing an arbitrary linear estimator, why don't we just take the one we started with and adjust the weights a little bit in a completely arbitrary way, and then see what weights we would pick if we were trying to make the variance of this new estimator as small as possible. So that said, in order for beta star, our new estimator, to be unbiased, it must be the case that C times X is 0, because we want the C X beta term to drop out. We must substitute away from Y. And we want the C times X beta to be 0, so C times X has to be 0. And it must also be the case that C times, the expected value of C times U is 0. So that we have a linear estimator that's arbitrary. We just change the weights a little bit. And we could pick the change from any way we wanted. And then derive the variance of this new estimator and compare it to the least squares estimator variance. And we're done. So it turns out that the variance of our new estimator is bigger no matter how we choose C. The variance of our new estimator is at least as big as the variance of the least squares estimator, because the variance of the least squares estimator is a positive definite matrix, and the variance of this new linear estimator is going to be positive definite, and it's the least squares variance plus another symmetric positive definite matrix. So it's always bigger. How do I know that when I'm all done and I have a CC transpose term in there, how do I know that that's positive definite? Well, to begin with, it's real, it's symmetric, and it's a covariance matrix. It has to be positive definite. You can't have a negative variance. Josh, is there a difference? Suppose that my error term, suppose I added another assumption and I said my error vector was jointly normally distributed. So, and I know it's a normal density. So from that, I derive my maximum likelihood estimator for beta. When I'm all done, would there be any difference between my maximum likelihood estimator and my least squares estimator? No. When you're just talking about a univariate random variable, isn't the least squares estimator, which is the sample mean, the same as the maximum likelihood estimator, which is also the sample mean? Right? Same thing. So why would it be different here? So the maximum likelihood estimator for beta hat is the same as the least squares estimator for beta hat. So Alex, we had that garden variety regression model. We have been told that the least squares estimator for beta is x prime x inverse x prime y. We've been told that the expected value of beta hat is equal to beta. We've also discovered that the variance of beta hat was equal to beta hat minus the expected value of beta hat post multiplied by beta hat minus the expected value of beta hat. Transpose was equal to sigma squared times x prime x inverse. And where do we get an estimate of sigma squared? Oh, the other thing we were told was that y minus x beta hat was equal to the least squares residual. Where do we get an estimate for sigma squared? We need it. the variance of beta hat is equal to sigma squared times x transpose x inverse. Remember I said that the Greek characters are population parameters which are not known to us. So isn't it the case that there's an unknown in the variance of beta hat? Yeah, sigma squared. We have to make a guess for that. We would like to have an estimator for that. So we need to figure out how we're going to construct an estimator for sigma squared. So how am I going to do that? Let's start. We're not going to do any dividing yet. I started off somewhere over here. We're trying to get somebody to substitute away from things. What's the random variable in this garden variety regression model? In my garden variety regression model, what's the random variable?
You can find variance. Why don't you do y minus y hat?
Oh, isn't that what this is? Okay.
Then you divide by.
Oh,
Then you divide by whatever.
I want to build sigma hat squared. And what you want me to construct is y minus y hat transpose times y minus y hat. What desirable property would we like to see in sigma hat squared? What two properties did we derive for beta hat? Been a long day. Unbiasedness and efficiency. Okay. So what did you want me to divide by here? 10 minus 10, right? Okay. So you assert that that's an estimator for sigma squared. And you've also told us now that you believe that you would like this estimator to be unbiased. So what we're interested in is figuring that out, right? So how am I going to figure that out? What's the random variable in my garden variety regression model? Why is y random?
Why is it random?
Yeah. Why is y random? Because y is equal to a non-stochastic part and a random vector. So isn't that why y is random? I don't know. So we're after the expected value of sigma hat squared. Is it readily apparent in this fraction where the random variable is?
No.
So why wouldn't I substitute away from the y's? From the y and the y hat? I would, right? I would do that. So that I could write sigma hat squared is equal to x beta plus u minus x times x transpose x inverse x transpose y hat. X transpose. I'm having trouble here. I'm having a brain freeze for a minute. Y hat. X times x minus inverse x times y. X beta plus u minus y hat, which is again x times x inverse x times y, all over n minus k. So I got u in there in one of the terms, right? Why don't I substitute away from y again? So I get sigma hat squared equal to x beta plus u minus